Hi, my name is Elena Gribelyuk. Today I'll tell you about our recent work on lifting linear sketches. This is a joint work with Honghao Lin, David Woodruff, Huacheng Yu, and Samson Zhou. Okay, so let's begin by defining the streaming model. We assume there's an underlying frequency vector x, which is initialized to 0. And the stream consists of updates of the form it, wt, and we should interpret this as adding wt to the itth coordinate of the frequency vector. At the very end of the stream, after processing it, the algorithm should output an approximation of f of x for some given function f. And importantly, the goal is to design an algorithm that uses space sublinear in the dimension n and the length m of the input stream. So in the streaming model, there are two important regimes to consider. One is the insertion-only model, where these weights wt can only be positive. This means I can only insert elements into the stream. And alternatively, there's the turnstile model, where the weights can be positive or negative, meaning I can insert or delete elements from the stream. Linear sketches are a very common and powerful method to obtain low-space streaming algorithms. A linear sketch is an algorithm that maintains a times x for some matrix A throughout the stream. And as we will see in this talk, it's very important that the entries of A should be poly-n bounded integers. So linear sketches are very helpful in the streaming model as they're easy to maintain under additive updates to the coordinates of x. And at the very end of the stream, or whenever it's queried, the algorithm would then output f of ax, where f is a post-processing function. In fact, through a sequence of works, it's been shown that all turnstile streaming algorithms on a sufficiently long stream might as well be linear sketches. And actually, all known streaming algorithms in the turnstile model are linear sketches. Now, lower bounds are fundamental to our understanding of capabilities and limitations of streaming algorithms. And a very popular method to prove such lower bounds is to define two hard distributions, D1 and D2, that have a large gap for some problem of interest. And then we show that the total variation distance between ax and ay is small when I sample x from D1 and y from D2, when the matrix A has at most r rows. So this allows us to conclude a omega of r lower bound for the dimension. Now let's look at a simple example for a problem we'll be focusing on a lot in this talk, the problem of estimating the L2 norm. Now let's allow D1 to be the distribution, standard normal distribution, and let's let D2 be the standard Gaussian but shifted by epsilon times the identity. Now, without loss of generality, we can assume that A has orthonormal rows. This is because we can always post-process by multiplying by a change of basis. So if we now sample x from D1, then because of rotational invariance, A times x is also distributed as a standard Gaussian with identity covariance in the r-dimensional space. And if I sample y from D2, I get that ay is distributed as a Gaussian with 1 plus epsilon times identity covariance in the r-dimensional space. And now at this point, using standard results on the number of samples needed to distinguish two normal distributions, we know that the dimension needs to be at least log 1 over delta divided by epsilon squared. So similar techniques have been used to imply lower bounds for many problems, including LP estimation, compressed sensing, eigenvalue estimation, operator norm and Kaifan norm, and also norm estimation for adversarially robust streaming algorithms. And it's true that these distributions, D1 and D2, are often chosen to be multivariate Gaussians or slightly shifted from Gaussian, maybe with a spike, to utilize rotational invariance. Unfortunately, a drawback of all of these lower bounds is that they really require the entries of the input vector, x, to be real valued as well. And this is inherent in the approach, because if x had entries with finite bit complexity, we could always use large enough precision entries in the real valued matrix A to exactly recover x from ax. And recall that the streaming model is defined on a stream of additive updates to x with finite precision. So these issues mean that none of the above lower bounds that I mentioned can actually be applied to the data stream model. Now, one way we might want to fix this issue is we could try to discretize the input distribution to any of these problems. However, there is some difficulty here as the distribution is no longer rotationally invariant, and it's really not clear what information about the input is revealed to the algorithm when we truncate these low-order bits. So the key question is as follows. Is it possible to lift linear sketch lower bounds for continuous inputs and obtain linear sketch lower bounds for discrete inputs? Now, another place where a similar issue comes up is in the adversarially robust streaming model. In this model, updates to an underlying frequency vector arrive one at a time, as before, but now we can think of them as being chosen by an adaptive adversary. So at each time point, the algorithm will receive an update from the adversary, and it will provide an evaluation of the given function on the prefix of the stream that it has seen so far. And the adversary records this response and then may select the next update depending on the previous responses of the algorithm. And importantly, as before, the goal is to design an adversarially robust streaming algorithm, which uses space sublinear in the dimension n of the input. Now, we have the adversary here on the left and the algorithm on the right, so let's look at an example. So let's say the problem is to estimate the number of non-zero coordinates in X. So at the first step, the algorithm will receive an update to add 1 to the first coordinate, and it will report that there is one non-zero coordinate. Now it will continue to receive updates. Now the number of distinct elements is 2, and so on. However, as the adversary is interacting with the algorithm, over time it may learn something about the internal randomness of the algorithm, and it may cause the algorithm to fail eventually. In the standard streaming model for insertion-only algorithms, we have had a long sequence of works that has now tight upper and lower bounds for LP estimation. And in fact, over the last few years, after the adversarially robust streaming model was defined, there have been several works that already showed that, roughly speaking, no losses are necessary in the space complexity if we require the insertion-only streaming algorithm to also be robust. Unfortunately, though, there's currently a large gap between the upper and lower bounds for turnstile streams. In fact, the upper bound is just the trivial O of n upper bound, where we store the entire frequency vector. And the lower bound is some polylog n, which comes from the standard streaming model for that problem. A very interesting work of Hart and Woodruff in 2013 showed that linear sketches for LP estimation are not robust to adversarial attacks, meaning that they require omega n dimension to succeed. And roughly speaking, the attack works as follows. The attack will want to learn the sketching matrix A. This is, in fact, the internal randomness of the algorithm. And then, after it learns, roughly speaking, this matrix A, then it can query X in the kernel of A, or it can query 0, each with probability 1/2. And this will be a hard distribution since the algorithm will not be able to distinguish these two. So the attack will proceed as follows. To learn the sketching matrix, we'll start by setting V1, the first subspace, to be empty, and we will iteratively learn more and more vectors in the row space of the matrix. So the first step will be a correlation finding step. This means that we will find vectors weakly correlated with the row space of A and orthogonal to all of the vectors that we found before. The next step will be a boosting step, so we will use the vectors we found earlier to find an even stronger correlated vector to the row space of A. And finally, we will make progress by setting the new subspace, Vi, to be the span of all of the previous orthogonal vectors that we found earlier, and also this newly found strongly correlated vector, V. So let's talk about a few features of this attack. The attack randomly generates Gaussian vectors to be used as queries in the correlation finding step that I described. And the analysis really requires the rotational invariance of these Gaussian vectors and only works for real-valued inputs. So this begs the question, does there exist a sublinear space adversarially robust F2 estimation linear sketch in a finite precision stream? Recently, this was answered for linear sketches for L0 estimation, but there the techniques are really specific to L0 and cannot be applied here. Our main contribution is that we give a technique for lifting linear sketch lower bounds for continuous inputs to get linear sketch lower bounds for discrete inputs. So this kind of answers all of the questions from the previous slides. This technique will be applied for both the standard streaming model and also the adversarially robust streaming model. Before I formally state our lifting framework, let's define the discrete Gaussian distribution, which is very important to us. Let D0 S transpose S be the discrete Gaussian distribution with zero mean and covariance S transpose S. Then the probability mass function is given as follows. So this is exactly the probability mass of a continuous Gaussian distribution with this covariance, except it's only defined at the integer points. Now, importantly, this does not satisfy rotational invariance anymore, and there's also a normalizing constant. So now we're ready to describe our main lifting framework. Suppose I sample X from a discrete Gaussian distribution with covariance S transpose S, and I sample Y from a corresponding continuous Gaussian with the same covariance, and let Z be an arbitrary integer distribution. Now, let's assume that the problem that I want to evaluate, F, satisfies this probability bound. So here what it's saying is that the probability of F of X being not equal to F of Y is very small, where X is sampled from a discrete distribution and Y is sampled from a continuous distribution. So you can think of this as some sort of smoothness condition on the problem itself. And in fact, this is already satisfied for all of the problems that we study. Now, let's assume that we have a very good linear sketch, G of AX, which is correct for discrete Gaussian inputs with high probability. And let's assume that the sketching matrix A has polynomially bounded integer entries and the singular values of the covariance are sufficiently large. This can be ensured easily since we're the ones choosing the covariance matrix. Now, if all of these bullet points are satisfied, then we show there's another sketching matrix A prime with 4R rows and an estimator H, such that there's this new linear sketch H of A prime Y is correct with high probability for continuous Gaussian inputs. So to summarize, what we show here is that if we have a good linear sketch for discrete Gaussian inputs, then we also have a good linear sketch for continuous Gaussian inputs, and this new sketch for the continuous Gaussian inputs only has 4R rows compared to R. Now, let's see how we can use this lifting framework to get a lower bound for our favorite problem, L2 estimation. So let's define this function f of x to be deciding whether the L2 norm of x is less than 1 plus epsilon times n or bigger than 1 plus 3 epsilon n. And we can return either of them otherwise. Now let's consider these distributions. I'll sample x1 from a discrete Gaussian with covariance n squared times identity, and x2 from a discrete Gaussian with a slightly shifted covariance. And I can similarly sample y1 and y2 from the corresponding Gaussian distributions. Now notice that it's not too hard to see that the function f satisfies that the probability of f of x not equal to f of y is very small. And now let's try to use the lifting framework to prove the lower bound. Suppose there exists a good linear sketch G of AX that can distinguish between the two discrete Gaussian distributions, x1 and x2. Then, if you recall from our theorem, there exists another linear sketch, H of A prime y, which can distinguish between the continuous Gaussian distributions, y1 and y2. But as we know, there is already a lower bound of log 1 over delta over epsilon squared for distinguishing between two continuous Gaussians. So this lower bound directly transfers from the continuous case to the discrete case, since the dimension of A prime is only a constant factor times the dimension of A. So using similar arguments, we can apply our lifting framework to obtain optimal lower bounds for a variety of problems, in particular for LP estimation p bigger than 2, operator norm, eigenvalue estimation, PSD testing, and compressed sensing. And also, we can use the lifting framework, albeit in a slightly more complicated way, to prove an optimal lower bound for adversarially robust F2 estimation for linear sketches. So let's let B be some fixed accuracy parameter. What we show is that any adversarially robust streaming algorithm which uses a finite precision linear sketch and B approximates the LP norm in an insertion-deletion stream must use roughly n rows. And our adaptive attack is efficient using only poly R log n adaptive queries. Now we're ready to talk about a high-level overview of the techniques for proving the lifting framework. Essentially, what we want is to simulate continuous Gaussian queries using discrete Gaussian queries. So let D sub ls denote the discrete Gaussian distribution on the support L with covariance S transpose S. And let's sample X from a discrete Gaussian supported on the integers Z to the N with this covariance matrix, and Y sampled from the discrete Gaussian supported on A times Z to the N with the corresponding covariance matrix after multiplying by A. Now, if we want to mimic the continuous case, we want to show some sort of rotational invariance. We want to show that the total variation distance between AX and Y is small on the support A times Z to the N. Now, to show this, we adopt techniques from lattice theory, and we look at this paper of Agarwal and Regev in 2016, which showed a sufficient condition for this small distributional gap. So supposing that some condition is true, which I'll talk about in a second, then it's actually true that the PMF of the distribution AX at a point Z is very close to the PMF of the distribution Y at the same point Z. And now if we set this epsilon parameter to be 1 over poly n, the sketching matrix will pass through to the covariance as we wanted. Now, to describe this condition a little bit more, L-perp of A is the lattice containing integer vectors which are orthogonal to the row space of A. And lambda max is the maximum successive minimum of the lattice. This is the smallest radius such that a ball centered at the origin contains the full basis for this lattice. Now, to summarize, the sufficient condition for showing closeness between the two distributions is that the minimum singular value of S is at least lambda max of the orthogonal lattice to the row space of times some polylog factor. And of course, we can scale S such that the minimum singular value of S is at least poly n. So in that case, we just want to upper bound lambda max of the orthogonal lattice by poly n, and then we would achieve this condition. However, this is not true in general for all possible sketching matrices A, so we will need to do something more to handle that. The key observation here is that we can always add more rows to the sketching matrix A and then prove a lower bound against that new matrix, as this would only make the sketching matrix stronger if it had more rows. So what we do is we design a preprocessing for this sketching matrix A, which outputs a new matrix with R prime rows, R prime being only a constant factor larger than R, such that now this condition is satisfied. Lambda max of the orthogonal lattice to A prime is at most poly n. Okay, so now that we have preprocessed our sketching matrix, we can assume that the orthogonal lattice to the row space of A has bounded successive minima. So in particular, the distributions of AX and Y are very close at all lattice points in A times Z to the N. However, these distributions may still be very far everywhere else. So to handle that, let eta be a uniform noise in one unit cell of the lattice A times Z to the N. Now, the final ingredient will be to show that the distribution of AX plus eta is very close to the distribution of A times Z, where Z is a continuous Gaussian with the same covariance as X. So we will show this through a sequence of steps. First, we show that the distribution of AX plus eta is very close to the distribution of Y plus eta. This follows directly from our preprocessing and by applying the theorem of Agarwal and Regev. Next, we show that the distribution of Y plus eta is close to the continuous Gaussian centered at 0 with covariance A transpose SA. And in fact, this is exactly the distribution of A times Z. So by linking all of these arrows together, we've shown that the distribution of AX plus eta is close to the distribution of A times Z, where Z is a continuous Gaussian. So you may now wonder, so real discrete sketches will actually just observe A times X as the input. So why was this useful? Well, we can always recover A times X from AX plus eta just by rounding inside of the unit cell of the lattice. So we can just assume, without lots of generality, that the discrete algorithm will see AX plus eta. And so the same algorithm should also be correct for continuous Gaussian inputs, A times Z as well. Okay, so now to summarize our contribution, we gave a framework for lifting dimension lower bounds from real-valued linear sketches to integer sketches. And the high-level idea was to use discrete Gaussian inputs in place of continuous Gaussians for certain well-behaved sketches. And as we showed in our paper, this method can be used to achieve lower bounds for a variety of problems in the standard streaming model, as well as for adversarially robust norm estimation. So some future directions in standard streaming could be to show lower bounds for streaming algorithms beyond integer linear sketches. And in the world of adversarially robust streaming, currently we already have attacks on linear sketches for L0 estimation and LP estimation in adversarial insertion deletion streams. So a prior work gave an omega of n to the little 1 dimension lower bound for L0, and this work gave a omega of n optimal lower bound for LP. So the next steps could be to show lower bounds for streaming algorithms for LP estimation and L0 estimation on adversarial insertion deletion streams. Thank you so much for listening.